Hello and welcome to my next video on FPL, the formal proving language. In this video I would like to concentrate on definitions in proof-based mathematics and how we can express them in FPL. As you remember from my last video, we defined proof-based mathematics as the part of mathematics in which we define mathematical objects, make assertions about them, and prove or disprove these assertions based on logic. So the whole process of proof-based mathematics starts with mathematical definitions. Mathematical definitions, in other words, are the basic building blocks of proof-based mathematics. And in this video, I will show you some real-world examples taken from different mathematical books where we can find definitions. I will also explain what these definitions are saying, basically, what they mean. But it is not important that you understand the mathematics behind these definitions. What I would like to stress is the semantics and the linguistics of these definitions rather than what the concrete mathematical meaning. Nevertheless, it is helpful to understand also the meaning of these definitions, so you can follow me on the features, linguistic features I am discussing. Let us dive in, and I will show you the examples I have chosen for this definition, for this presentation. Okay, so these are the examples I have chosen, and I hope you see my mouse here, because it is important that you follow me what I'm talking about. So the first definition is from Edmund Landau. Landau was a German mathematician, and he wrote Foundations of Analysis in German. It is an English translation I have from 2001 from Bowo Press, and it says in the definition 2, if x equals y plus u, then x is greater than than y. And it puts also something in parentheses how to read this symbol which is greater than. So basically this definition defines the symbol and the relation between the being greater relation between two other symbols, and the reader has to know, which is clear from the context when you read the book. It is not clear here, but the context of this definition is that you have to know that these symbols x, y, and u denote positive integers, natural numbers. So basically, this definition says that if then a positive integer u exists, such that to build x, we have to add to y this positive definition, positive integer u. If this is the case, then x will be greater than y. So this is the mathematical meaning of this definition, but as I said, you don't have to follow the mathematics behind it. The linguistics is more important for me today. And as you can see is that we have some symbols, and this definition defines the symbol being greater than between other symbols, and provides some explanation why we can put such a symbol between other two variables. The next definition is taken from Basic Discrete Mathematics from World Scientific in 2016. And this is the definition of geometric sequence, which says a sequence t1, t2, t3, ... is geometric if the ratio tn divided by tn minus 1 between any two consecutive terms is constant. So let us dive into the mathematics behind this and then to the linguistics. The mathematics behind this is that it is defining a sequence of numbers, and when this sequence of numbers is geometric. So you have to know what a sequence is first before defining what is geometric, what a geometric sequence is, because otherwise you don't know, you don't understand what a sequence T1, T2, T3 ... is. But once you have understood what a sequence is, you can read this definition and see, okay, sequence T1, T2, T3 is geometric in the case where we can put create such a ratio, and we have such sub indices here, Tn, which is one term, and Tn minus 1, which is the previous term before the Tn term. So we have exactly what is being said here between any two consecutive terms. These are the consecutive terms here. And if this ratio is constant for all these ratios, regardless which two consecutive terms we take, then the sequence is a geometric sequence. So as you can see, this definition is based on many different other mathematical concepts like sequence, like ratio, like consecutive terms, like constant. We have a formula which is explained in prose text. So the same formula is explained here. Basically, what this formula means is exactly what this explanation is, and this is a new definition. Then we have the third definition. Let A be a set, taken from Charles Pintar's a book on set theory. Let A be a set. By the power set of A, we mean the class of all subsets of A. Now, the next sentence starts with, in symbols, the power set of A is the class. So this formula here, I don't want to read it. What I want to stress instead is that we have a definition which is first formulated in prose text. Of course, there are some symbols like the symbol A here, but we have a whole sentence which is formulated in prose text, and then in addition to this definition, we have a new definition which is put in symbols. And this part here, in the second part of the definition, is exactly what has been said in prose text. So you have a definition which repeats what is the same mathematical concept and formulates it first in prose text and then in symbols, but both express the same. So this is another kind of definitions we can find, for example, in many different books. Then we have yet another last example I wanted to show you today. But as I said, there are millions and millions of different types of definitions we can find. But I have purposely chosen these four because I want to stress some very important fact about how we can classify definitions in proof-based mathematics and why it is important to classify them like this, because this became a requirement for writing FPL and programming FPL as a language to express proof-based mathematics in an artificial way. So coming back to our last example, A space is totally path while disconnected. Okay, the example is from counterexamples of typology, Dover Publications, 1995 by Steen and Siebach. A space is totally pathwise disconnected if the only continuous maps from the unit interval to X are constant, or equivalently if its path components are single points. Again, you don't need to understand the mathematics behind. What I want to stress here is the linguistics of this. First of all, we have a new concept, which is a totally pathwise disconnected space. So you have to understand what a space is before you can read the definition of what a totally pathwise disconnected space is. Once you know what a space is, you can then read the rest of the definition. If the only continuous maps from the unit interval into X are constant. So you have to understand what is continuous map, what is a unit interval, what is X, and what are constant. From the context, you would maybe when you read the whole book, you could conclude that X stands for the space we are talking about. But it is really a quote from the book. It is not. I haven't changed the text. This is really a quote from all these books. All these examples are quotes. So what I want to stress in this fourth example is that we have a new alternative, which is totally different to the alternatives presented in the preceding examples. Remember, we have alternatives here being, for example, here between the two consecutive terms is an alternative explanation of what this formula means. Here, this sentence in symbols, the power set this with a formula expresses the same as an alternative, expresses the same as has been said here in prose text. But now we have a totally new kind of alternative. What the authors provide us here with is, or equivalently, if its path components are single points. So it is not a new formulation of what has been said so far in the first part of the definition. It is another concept. As you, if you understand the mathematics behind, you will immediately see. But if you don't understand it, please believe me just that these two parts of the definition have two different types of concepts in them. If path components are single points is a totally different thing as saying if its path components are single points is a totally different thing as saying if the only continuous maps from the unit interval to X are constant. Usually in mathematics, such equivalence between two different concepts is a theorem. It is not a definition. You have usually you would provide the reader with two definitions. The first one looking like this, and the second like looking at this, and then formulate a theorem that these two definitions are equivalent by showing that whenever this condition is fulfilled, it follows that this condition is fulfilled, and then showing that if this condition is fulfilled, it follows that logically that this condition is fulfilled. And after you have proven both directions, that these conditions follow from each other, you would be able to say that they are equivalent. But in this example, our authors provide us with an alternative way of defining totally pathwise disconnected spaces in topology, and the reader has to, yeah, basically she has to believe it or not, and take it for granted. So why is all this important? Why have I chosen all these examples, and why am I talking all the time about the linguistics of these definitions? I want to show you that in proof-based mathematics, first of all, there's a lot of unpack to unpack here. First of all, you can see that there is no standard way of defining things in proof-based mathematics. There is, for example, there are many differences of what is being defined here. When you see about when you look at the symbols here, in this first definition, we have to know what the symbols what the symbols denote from the context. What is the domain of discourse? What we call in mathematics the domain of discourse of this definition. So you can understand what these variables mean. In this, for example, in this definition, we have a notion: let A be a set. So we know that A has to be a set. A is a set. There is no such notion here that let X, Y, and U be natural numbers. The author leaves this notion out here, but this author provides us with the notion. Again, as far as symbolic notation is concerned, we have here in this definition no symbols at all, unless we take this X and conclude that the authors mean maybe the space they are talking about. So there are differences in symbolic notation. There are also differences between the markers which start with a definition keyword. So when you read such books, you have many times you have a keyword definition. It is numbered maybe. So this is the second definition in this book, Landau book. This is a 6.1.9th definition in this book, and this is the 1.49 definition in this book. But there are books also which are counterexamples of this. Occasionally, you will find books without such markers, and this is funny because this book is titled Counterexamples in Topology, but what I mean by counterexample is not the title of the book, but the counterexample in linguistics, that there is no marker saying that this is a definition. It is a prose text, it is a flow of text, and in this flow of text, the only thing that you think that this is a definition is how the authors highlight what they are being defined, what is being defined. So we have here a bold font, and then we know that this is the definition. In this case, we have italic font. So we know, okay, this is what is being defined. In this case, we have in parentheses the name of the concept which is being defined. And in this case, we have in parentheses how a new symbol has to be read. So there is no difference, so there's no standard way to define things in mathematics nowadays. And nevertheless, because although there is such a great variety of definitions in nowadays books, there is only one thing you can be sure that we can say about what is common in all these definitions. And one thing which is common is, and the only thing maybe which is common, is that there are 3 and only 3 types of definitions we can find in proof-based mathematics. There are definitions which define mathematical objects. There are definitions which define predicates, and there are definitions which define so-called functional terms. Okay, what are all these 3 types about? When you think about this definition here, this one defines a geometric sequence. So geometric sequence would be a definition of a mathematical object. It is a sequence, and this is a geometric sequence. So this is an object which is being defined here in this definition. So we can then write theorems about geometric sequences, for example. Then we know about we know what we are talking about. We are talking about the mathematical objects called geometric sequences. It is not the case in this one and this one, in this definition and this definition, because these definitions do not define mathematical objects. This definition, the first definition, defines what we call in mathematics, or better to say in logic, a predicate. A predicate is something, is an expression which you can interpret, and then you get the answer yes or no. Whenever you are able to say to a relation whether it is a true relation or a false relation, then you have a predicate. So, for instance, if x is greater than y, or the expression x greater than y is either true or false. This is why this definition is a definition of a predicate. It doesn't define what a natural number is. It doesn't define what this geometric sequence is. It doesn't define any mathematical objects. It defines the relation between 2 different mathematical objects, and this relation, whenever we have this relation later in the text to come, whenever we read this relation, it is either true or false. Whenever this is the case, we have a predicate. So this is a definition which would classify as a definition of a predicate. The third type of definitions I have been talking about is a so-called functional term. A functional term is different, is yet another type of definition. It is not a mathematical object. It is not a predicate. A functional term is an expression in which you have if you will, an input, and then you get an output. Please do not confuse functional terms with functions in mathematical sense. They are not functions. What I mean by functional terms is a linguistic term. It's a linguistic concept. Functional terms is a linguistic concept. And a functional term has an input and an output. And the input in this case is the set A, and the output is this set here. And the main idea of functional terms is that whenever we define something as a functional term, this new functional term cannot exist without its input. It doesn't make sense in this example, for example, to talk about the power set on its own. It only makes sense to talk about a power set of another set. So this another set is an input which is required to define the power set, because otherwise it has no meaning. And this is what characterizes functional terms. And this is why this definition here is an example of a definition of a functional term. So we have three different types of definitions in mathematics. We have a definition of predicates, we have definitions of objects, and we have definitions of functional terms. Why do we know that there are only these three? Because it is not something that I have found. It has something to do with how logic can be defined and in which different levels logic can be formalized. And I will produce some other videos on this important topic, because we have to also to understand what when we talk about formal proving language, you have to understand which type of logic is possible to express in this language. And there are at least three different types of logic. There's zero level logic, first level and second level logic, and there are many more, third and fourth and so forth. But these different formulations of logic are necessary for formulating proof-based mathematics, and a lot more intelligent people like me than me have thought about this problem, how to formalize mathematics in the 20th century, and they have developed different types of levels of logic, and in the course of this definition, they have found out that definitions have to be that there are only three types of definitions. Definitions of mathematical objects, of predicates, and of functional terms. And if you have such a syntax which is capable of defining functional terms, if you have symbols for functional terms, for predicates, and for mathematical objects, then you basically can formulate a lot of proof-based mathematics. So what kind of into which of these three classes we would take this one? This one is kind of different than this one. This is neither. It seems to be neither a definition of an object, nor a definition of functional term, nor a definition of a predicate. But when you think about it, it is a predicative definition, because a space is either totally path disconnected, or it is not totally pathwise disconnected. So we have again this example of answering a question whether something is or is not by answering yes or no, or true or false. So this is a predicative definition again. Nevertheless, it is a slightly different as at least these two ones, because it is defining a property of another object which has been already defined. A space, you have to understand what a space is to read this definition. So you have to, in this book, you will find another place where they defined what a space is. After defining what a space is, they are ready to define a particular space, which is then totally pathwise disconnected. And what can be said about such a kind of definition is that it is predicative, but nevertheless it is not defining an object, but it is defining a property of this object, which itself is a predicative one. So to summarize all of this, I want to show you this summary. When we talk about definitions in PBM, in proof-based mathematics, and surprise in FPL, in formal proving language, which is designed to express proof-based mathematics, we have to distinguish between three different types of definitions: between definitions of objects, between definitions of functional terms, and between the definitions of predicates. And once we have done this, we have the definitions of an object, for example, and this definition can be extended by properties, which themselves can be predicative or functional term wise or object wise. The same holds for functional terms. When we define a functional term, we can define objects which are properties of these functional terms, or other functional terms which are functional term properties of these functional terms, or predicative properties of these functional terms, and so forth and so forth. So we have properties and we have basic definitions. And all of these definitions and properties have only three classes: objects, functional terms, and predicative properties. Maybe one last example to understand it. Let me say, for instance, you may remember from school that you have functions and you have derivatives of these functions. And or let me say this example: you have a function, and you have defined a function in school, and then you talk about what a continuous function is. So once you have defined a function, you have defined an object. Okay, the object is the function, but being continuous is a predicative property of this object. Okay. Maybe another example: we have a greater than predicate. Okay, and then we can say, okay, this greater than is an order, and this may be partial or not partial. So there are properties which can be predicative for the predicates. Or we yet another example. Let me say we have an object that is an object like, for instance, a natural number. We have the object is natural number, and then we have a property, which is a functional property of this object, the successor of the natural number. So each natural number would have an object, which is its property, the successor of this natural number. This would be a functional term property, while the property that a natural number is even, so divided by 2, would be a predicative property. And we could also define an object property of the natural number, which is the negative counterpart of this natural number, for example 2 and minus 2. And this negative inverse, what we say of addition of this natural number, would be an object property. So they are always, all the time, we talk about only these three classes of definitions. We have object definitions, functional term definitions, and predicative definitions, and all these things we then define can themselves have properties which themselves can be object-like, functional term-like, and predicative-like. So this is the theory of different definitions, and let me now show you finally how to write all this in FPL. And okay, I've opened an FPL file, and my language server is running. So so I can see here, okay, it is there, and then I can show you how to write definitions here. And I don't want to express all these examples again, because then I would have to define what is a sequence, what is natural number, what is things like that. So all these mathematical concepts that are a prerequisite in your understanding to define these objects from my examples, I would have to also define here, and this is what I don't want to do this in this video, because it would be too much. Nevertheless, I want to show you that FPL is capable of making and create definitions exactly of these three kinds. So you have definitions of objects, which we are called in FPL classes. Then we have definitions of predicates, and we have definitions on functions. And I will insert them here, because this completion service allows me to take some templates. As you can see here, we have some example definitions here, and the class definition, the object definition defines something with a name. Then we have a type of this object, which there are some predefined types, but of course in FPL I will show you later in future videos how to define your own defined types, user-defined types, but there are some predefined types. And all these definitions are intrinsic. What this means is also something which is worth a separate video I will produce in the future. But nevertheless, these are the keywords which are important here. We have a keyword definition, then we have the type of definition, which is either class or predicate or function, class for objects, predicate for predicative definitions, and function for functional term definitions. As you see here, the functional term definition has an input, which would be put in this parenthesis, for example, and and then we would have an output, but also this is also allowed without an input, just an output. And there is a short version of this. So FPL comes with long versions of many keywords in FPL have a long version as a short version, and the same. This definition here in the long version of keywords is the same as this definition here. This is a short notation. The predicative one has also some short form, and this functional term definition also has a short form. And it is also the difference between these two is only what is more readable for you as a user of FPL. Some people like the short notation, some people like the long notation. I personally prefer the long notation because it is more readable, but of course you can put this also like this. And the most important thing I want to take you to take from this video is that there are three types of definitions: objects, predicative, and functions. And all these definitions have also it is possible to define for each of them. It is possible to define properties. Okay, so there's a property of object. It would be here property of a predicate, and we would have a property of a function inside this definition. So think about my example of a natural number with a property which is an object property would be, for example, what was the example? Predicative was the example that we have an even number. And even number, what is an even natural number? It would be a number which is divisible by 2. So we would put this divisible by 2 here in this property, and instead of saying intrinsic here in the definition here, we would say what is a natural number. So we can basically provide extend definitions of objects, of predicates, and of functions by such properties, and this is possible in every type of this. We can put such properties also in predicative definitions, and we can put such properties in functional term properties definitions. So this is basically what I want to give you as a takeaway from this video, that it is possible to that FPL enables us to define different things, and these different things are exactly 3: objects, predicates, and functional terms. And we have properties also from these 3 types of these 3 types. And so basically this is it for this video. I know this is a lot of stuff and a lot of theory and lot of linguistics. It is quite complicated if you think about this. Nevertheless, you have to go through this process if you define a language like FPL, because otherwise you will get lost in basically in the principles of how to express proof-based mathematics if you don't provide the possibility of expressing different things which are possible through that variety of definitions we have seen in only these 4 examples. And as I said, there are millions of such examples and millions of different possibilities. But all of these possibilities can be classified and put in a standard way, only using 3 different types of definitions we have in FPL. So thank you very much for your attention in this video. I hope you have enjoyed it. Nevertheless, although it was highly challenging in maybe not in mathematics or maybe mathematics also, but also in linguistics. And if you like such a content, please give me a like, and I hope you will see and visit my next video. I will be talking about logic and how FPL is capable of expressing second level logic. So see you later. Bye.